Okay, so good afternoon, everybody. Welcome once again to the Escape Summer School. And this last session of today, it will be on packaging and distributing Python projects once more with Max. Okay, Max, you cannot hear me. I don't know. Okay, I think in any case, you can start, Max. If I will confirm that we can hear you also through in the streaming at YouTube in a moment. Okay.
Hi, Enrica, I couldn't hear you. Maybe it's a problem on my side, but
we're just saying that maybe you can start.
Can you hear me? Sorry, can you just?
Maybe you should with Enrique microphone, but
okay, nice. So I will
we
go
can
ahead.
hear you, so that's
the problem was on your side then. So I will talk about packaging and distributing Python projects, and that will basically mean we want to publish our Python projects. So we are now in the realm of well-tested Python packages that are published on GitHub. But what we now basically want to enable is that people can pip install or conda install our packages. And we will go through what packages are, how you have to structure your code to make them packages, and what you then have to do to really upload them to one of the providers, hosting providers, so that people can easily install them using pip or conda. And this will take about an hour to give you one quick introduction to this, how we can do this. So again, we have a detailed overview here. So the current standard solution for doing this, publishing Python packages and make them installable, are the setup tools. And we will go over in detail what feature setup tools provides for you to write your Python packages and how you can then build them into the formats the different providers need to being able to publish them. Then we are very shortly talking about how you should choose version numbers for your projects. And there's one standard which is really helpful for that, which is called semantic versioning. And we will talk a bit about that. And then we discussed a bit in the open source section, or in the reproducible science section, about that we should publish our research code as open source code. And I will talk a bit about what that actually means, what kind of software licenses we can give our code, and how we can include that for our Python projects. And especially for scientific code, Tamas talked a lot about how Python can be slow for, or is slow for, these heavy numeric computations, and that we have to rely on compiled code for that to be fast, for example, using C extensions or C++ code, or the special number JIT compiler. But if you have compiled parts in your code base, like a C extension, or even Fortran, like NumPy uses in some places, it's mostly not very useful for users if you just publish your source code, because if they then download the source code, they need to run the compilation again, and that can be quite hard to get right if you have a more complex compiled code base and you need all the binary dependencies and so on. And so there is a standard in Python that enables you to publish already compiled versions of your code to PyPy, and then users can just download the already compiled versions of your code and don't need to worry about if they have all the dependencies that are needed to build your C project or your C++ library, and they can just pip install a binary wheel, which is the standard we will be talking about for your compiled software. I want to then quickly introduce a new alternative for managing dependencies of Python projects to setup tools, which is called Poetry, which is a rather recent addition to the Python packaging landscape, which has some nice properties that setup tools currently does not provide. So I will briefly go over that. And then we will talk a bit about how we can actually create conda packages, because I mean, in this school, we now always use this Conda package manager and installed Conda packages from Conda and from Conda Forge. And I will explain a bit what this means and why Conda packages are a bit different than the regular Python packages, and how you then can create Conda packages for your Python packages. So this is basically a requirement for creating a Conda packages. First, to have this setup all working, and then we can also very easily create a Conda package for our Python package. And then in the end, I will give some general recommendations and conclusions. Okay, so again, I think you all know this slide by now. Please don't copy code from PDF files, it's dangerous. Type it by hand. Use the example files provided in the repository. So let's first talk about what happens exactly when you type in pip install a package. What that means is this command line utility pip that comes with Python when you install Python will search for that package on the so-called Python package index. And this is a website or web service that hosts storage and a website and a web service for installing these Python packages. And we can have a look here. So if we go to pypy.org, we will go to this package website here, and then we can, for example, search for the numpy package, and then it will list different versions of numpy. So the first hit here is the numpy, the current release of numpy 1.20.3. And then we see this short project description here, and we can also look at the different versions that were released. So there's already some pre-releases for the next version on here, but the current stable release is this 1.20.3, and then there are all the older versions of NumPy also available. We can manually download files here, which have some cryptic names here, which we will go over in detail later. But then, yeah, this is basically the website pip is talking to if we type in pip install a package name. So it will search for the package on this web server. It has an API where pip can talk to the server and ask what packages are available and what versions of the package are available and so on. And it can also get all the dependencies. So for example, if we talk about a project like Pandas, which is a very high-level data analysis software package, it will build up on other packages lower in this so-called Python scientific data stack, which you have seen in Tamas library overview talk. So there's basically this onion structure of packages building on top of lower level packages, and these are the dependencies. So for example, Pandas depends on NumPy and Matplotlib. NumPy for the efficient array structure and Matplotlib for visualization. So Pandas, if you say pip install Pandas and don't have NumPy installed yet, pip also installs NumPy for you because it knows from the metadata on PyPy that the Pandas package also needs the NumPy package. And we will be playing around here, and we are developing our project for the Fibonacci numbers further, and we want to publish it now. But really, this is a toy project, and during testing, stuff can go wrong. So the Python people know this. So there's not only the official pypy.org, but there's also testpypy.org where you can test if your setup is working and if it's producing a nice package and how it will look before you can really upload it to the official PyPy so people can pip install it. So there's also this testpypy.org. And this is the test Python package index where you can test your Python publishing workflow if it works. And when you made sure it works, you can then change the URL and not deploy to test PyPy anymore, but deploy to the real thing. And the software that runs on the PyPy servers is open source. It's called the warehouse. So you can also self-host a Python package index, which might be interesting for you if you're a big research institute or a big company, and you don't want to enable people to just install any kind of software, but you want to make sure that only like dependencies that you have acknowledged to work or that you have audited to work correctly are installed by your developers, and then you host your own PyPy instance, only include the packages that are allowed in your company or in your institution, and then people have to install packages only from that, from your own package registry, and which obviously also can be used for not open source code. So I won't go into any detail because I think research code has to be open source and must be open source for reproducible open science. So we will use the official PyPy for publishing our open source packages under an open source license. And then we have to talk a bit about the what that actually means to upload a Python package. And there are two main formats, and one is a very unstructured historical format, which is just a tarball or a zip archive of all the source files of your project. And this is very simple. You have your repository, you call tar, or you can even ask GitHub to create this tarball for you, and you upload it to PyPy. And then you have the problem that this is not really a standardized format. It can have basically anything inside, and it makes this dependency resolution harder, and you have to somehow check in the package code which system is actually used to build the package and so on. And these are all problems that were solved by the introduction of this wheel format. And you might wonder about the name, and this goes back to the history of Python. So when you nowadays look at all the things surrounding Python, you might get the idea that Python actually comes from a snake. And this is not true. So the Python logo has snakes in it, and all the different things like Anaconda or Mamba also make you think that Python comes somehow from a snake. But actually, when it was developed, and you can see this in the documentation in all the examples, Monty Python was the inspiration for the Python language, or this British comedy group. And this British comedy group has a very well-known sketch. You can check YouTube later, which is called The Cheese Shop. And because for Python programming language users, the cheese, the important stuff is the Python packages, you can go to the cheese shop, which is PyPy, and buy these or download these wheels of cheese, which are the Python packages. So this is was introduced a couple of years ago to improve the Python packaging situation, and it has done so immensely. I would say this is a really, really huge success and a big improvement in the last recent years. And this is a standardized format with predefined files inside where metadata about the projects is stored that store all the dependencies. For example, there's a file in there that where in a standardized way the requirements of your package are defined, and all the metadata that is displayed on PyPy, for example. So if you look again to the numpy example, so let's go back to the official PyPy for the numpy and go to project description. You see this short description here, and then you should see all these links to the home page, to the documentation, to GitHub where the source code is developed, and you see the information about the GitHub repository and which license and the maintainers and much more meta information here. So which versions of Python are supported by NumPy and so on. And these things are all defined in the packages in these fields using well-defined metadata fields in those fields. And what's special about the wheels as well is that they, like I mentioned, they cannot only contain the source code for your Python files, but they can also contain compiled C code or Cython code or wrappers for C and C++ libraries compiled for use on Linux, on macOS or Windows. And then you don't have to compile the software, but you can just install the pre-compiled versions from PyPy, and it's much easier to use packages that offer these pre-compiled wheels. And NumPy is one of the most well-known example where even on Windows nowadays you can just pip install NumPy and you don't have to have any C compilers installed. It will just download a working Windows pre-built binary version of NumPy. So these wheels have a problem in that it's a bit complicated to really build them so that they work on many systems, especially on Linux. Windows and macOS are easier because there's at any given point, at least now where Windows 7 is also out of support, there's only one version of macOS and Windows really supported, and then you can compile for that version and everything will work fine. But at any given time, there's a huge number of different Linux distributions around with different compiler versions and different versions of the C standard library. And to make sure that your package works on many of these Linux systems, you have to basically compile against the oldest supported version of the C standard library and other system packages you might rely on. And we will get to this later, but this is basically the reason why it's not that easy to publish compiled code on PyPy, because you have to make sure it really can run on many systems and not just on your own computer. Okay, so let's go right ahead. I have some example projects again in the school repository that use setup tools to do this. One simple example with our Fibonacci code, and then a second example using Cython to create a compiled C code extension for Python, where we will use the tools to create those binary wheels later. So setup tools is now the recommended tool by the Python packaging authority to create Python packages. There is a deprecated module in the standard library called distutils, which should not be used anymore. Setup tools is just much better than distutils, and I suspect that either setup tools goes into the standard library in the next time, or that because it's so easy nowadays to just get it via PyPy and the things we will later see. Anyways, every project should not nowadays should probably use setup tools and not distutils, or one of the newer alternatives. And it allows you to declare package metadata, to declare your dependencies, and it has the tools to create the files needed by PyPy, so you can publish your packages. And we will learn about many of these features of setup tools during the next couple of minutes. So let's talk about the structure of a Python package. So let's look at this eSchool21 demo, which is the more simple example. And we have seen the structure before, but now I will really go into the details why this is structured this way. So we have our base repository, which is called eSchool21 demo. And this is the Git repository in the case of a real package file. I mean, this is now inside the school repository, but for a real Python package, you want to have your own GitHub or Git repository, and then you have this base repository, which is the GitHub Git repository. In the base repository, you have a directory called eSchool21 demo as well, and this is now the name how you will import your package. So this directory name here specifies what you have to type to import your package. So in this case, this would be eSchool21 demo. And inside this package, we have our tests, and we have our init function, which is the entry point for each Python module. So every time I now type import eSchool21 demo, I'm actually using this init.py here in this directory. And then I have another module with the actual Fibonacci code, and that is now a so-called submodule of this eSchool21 module. And to import stuff from here, I would do eSchool21 demo.fibonacci, and then .fibonacci probably because inside the Fibonacci.py is a function called Fibonacci. And then there's a lot of files here in the space directory, so in the root of our Git repository. And this is a license file, which has our open source license for our project. And we will talk a bit about which licenses you can choose for your code later. And then there are a couple of files which are specific for Python projects. So this pyproject.toml is a rather new addition to the Python packaging landscape. I think it was standardized 1 or 2 years ago, and this is now used to really specify how your project needs to be built, what software needs to be available, to even create your package. And then there's the two configuration files for setup tools, which are setup.config and setup.py. And we will learn in detail later what we have to put in those to make our project work. Okay, so this is the summary again. README is our project description, and this is what GitHub will render as the first page when people come to our repository. License is our software license. PyProject is this common configuration for all Python projects. This is basically the first file you need to create when starting a new Python project. And then setup.py and setup.config are specific to setup tools, and we will get into detail what we are doing with them now. So let's first get the PyProject out of the way. So this defines the build time dependencies of the Python package. So this is not something your users need to use your code, but this is something you need to create the package before uploading it to PyPy, to create the wheel and to compile your software if you have any compiled components. And I don't know how much you know about how Python is actually developed, but similar to issue trackers for many projects, there are so-called Python enhancement proposals, which are proposals which are then discussed by the Python developers how to improve the Python language. And this pyproject.toml was defined and extended in these two Python enhancement proposals here, 517 and 518. Can also just look at those. So this is PEP 517, a build system independent format for source trees. And this basically defines this pyproject.toml. So for example, here we will see different examples for this pyproject.toml, what it can do, and so on. And there's 518, which also goes into more detail about this pyproject.toml. This is very technical, so if you're not a Python expert, you might not understand much of what is going on there, but these are really the sources for this kind of information if you want to have a deep dive into what this means. And pyproject.toml is nowadays not only used for this build time system dependency specifications, but many tools useful for Python projects also use this for their configuration. For example, there's this black formatter, which can convert your code into code that follows the Python style guides automatically. And this can also be configured to some degree in this pyproject.toml. But for our Python project using setup tools, we basically only need 3 lines here, which is this build system group. And then we say that we require setup tools and the wheel package to build our project, because we want to use setup tools and we want to create these binary wheels or source wheels for our project. So these are the 2 packages from PyPy we need to create our package. And then we need to give any tool that wants to build our package, this can be pip or the build tool we will see later, the information which function needs to be called to build our project. And in this case, this is the setup tools.build meta function, which will be used to really create our project. And then we can have a look into the configuration of setup tools itself. And for a long time, people wrote these setup.py files and put many meta informations and even code that did some stuff needed for the setup into these setup.py files. But people generally agree that having configuration in code files and not in some data format files is a bad idea, because it can generally run arbitrary code, and you have to trust that that code doesn't do any stupid things on your machine and it's not malicious and so on. So it's general better to use a static configuration data file and not some form of code. So nowadays you can basically add any information about setup projects to a setup.config file. But for these editable installs we also used in the testing lecture, you still need a minimal setup.py. And currently there's also a bug in pip which requires us to make a workaround. You don't really have to understand what's going on here, but there's an issue for pip here, and this is solved by adding this line here. So yeah, so just add these 3 simple lines of code to your setup.py, and then you're good to go, and you never need to touch setup.py again until this bug is fixed, and then we can happily delete also this line, or setuptools is updated to not require the setup.py for editable installs, and then we can hopefully in the near future get rid of the setup.py file completely. But at the moment we still need this. So these 3 lines of code need to go into your setup.py. Okay, and then the interesting stuff happens in setup.config. This is an ini style config file. So we have these sections here. We can add metadata about our project. So we can give it a name, a version, a short description, and the name of the license. And we will see what MIT here means a bit later. And then we can also give a long description, and this can be read from our README. So it's very common to not give here a long description again, but just to include what is written in the README. And then we can also specify, or we need to specify in what format this README is written. So by default, Python assumes that our READMEs are written in this restructured text, which is used for the Sphinx documentation, but it's more common on GitHub that you use Markdown README files. So we have to tell Python here or setuptools here that we actually use this text Markdown format for our README file, so it's rendered correctly on PyPy. And then we can also add classifiers. There are a lot of classifiers. These are basically these metadata bullet points you saw on the left side of the NumPy repository a couple of minutes ago. And we can add further options here. So this is the part where we add our requirements and our code files. So we can tell setuptools to automatically look for Python packages in the current directory using this find statement here. And we can say that our packages requires at least Python 3.6 and that we require AstroPy in our module, which is for the simple example project not really true, but I wanted to show you how you can require different packages here in this section. We don't actually need AstroPy to calculate Fibonacci numbers. Okay, and then we can build our project. And for this, we need this build module, which is also included already in the eSchool 21 environment. And then we can just call, sorry. We can just call this build function here. Python -m build will run the Python module build. And this will produce us our 2 formats of the packages. So it will give us a wheel file and the source tarball. And this is what I will show you now here. So in the school environment, we have the packaging directory, and in there we have 3 directories, one for the slides and 2 demonstration projects. And the first one is a more simple one. So we go to the eSchool 21 demo directory. And there we have basically all the stuff I showed you before. This is, let me just clean this up using a git command. So this deletes all the file not in the repository. So this is what the clean state looks like here before I run any of the build commands. And now we have these files I showed you before. So we have this eSchool demo directory and the license file, the README setup config. In the setup config, I have some more entries than I showed on the slides. So there's some more information here. We can later also talk about optional requirements and console scripts, but that's basically it. And then I can first run pip install -e dot to get this editable install, and that now works nicely because I have the setup.py and the pyproject.toml. And I also can run this build command python -m build. And that will then download the build requirements specified in pyproject.toml and create the source distribution and the wheel file. So we have now in this directory the 2 files, eSchool demo ending on the .bhl extension, which Python uses for this for these wheel files, and this tarball, which is the source distribution. And actually, a wheel is only just a zip file, but with a standardized content. So we can actually look at the content of this wheel file here using the unzip command. And I'm not unpacking it, I'm just looking into it here, and we can see that all our code is inside there. So our init function, our Fibonacci, and something we will talk about later. But there's also this special directory here, which has our version number inside it, and then has a license, a metadata, a wheel, entry points, top level.txt record. And this is something you don't have to care about, but it's specified in this wheel standard. And this is what PyPy is using to display the metadata and resolve the dependencies and so on. So this is part of this wheel standard that wheels need to have this directory here and these files, special files here, which were created by our build system when we executed the Python -m build command. Okay, so now we are basically done. We have our package. We have it in the dist directory, and now we want to upload it to test PyPy. So we install another tool, Twine, which should also be already available in the school environment. If not, you can run pip install Twine, or the recommended version, which is a bit longer, with Python -m pip install Twine, which makes sure that the pip actually matches with the currently used Python version. So if you use it like this, you are sure that you're not using some other pip somewhere else, but the pip that really belongs to your currently active Python installation. And then we can just upload it. So the command I gave here now uses the test PyPy repository and not the main PyPy repository, because I mean this is live demo. So let's just do this. I think I have to increase the version number because I already tested this and set up and PyPy does not allow you to upload the same file twice. Okay, so I have to increase my version number here. And we will talk later about why I specified the version number here in this init.py and not in the setup.config file itself. But I will now bump this to 0.2.0 and then run Python -m build again. And then I have also the 0.2.0 files here. And maybe to make sure I'm not doing a mistake, I will delete the old files here. So everything's 0.1 should be gone now. Yes, we have only the 0.0 files now, and let's just upload them. So Twine upload -- repository test PyPy, and then every file in the dist directory. And I have to give my credentials here. And then this is uploaded, and I can look at it directly in my browser. So here we have now freshly published on testpypy.org. We have our Python module eSchool21 demo. And PyPy even tells you the command you can use to install this Python package locally. So if I copy this command and go back to my shell and just go somewhere else or open a new terminal in my home directory and gonna activate eSchool 2021 again, copy the command. This has now installed the package we just published from PyPy, and I can also now import it here. So import eSchool 21 demo, and then I can use the Fibonacci function from this demo. Nice. Okay, so we just published our first Python package to, in parentheses, test PyPy, and everyone can now install it. if you want to, you can just go ahead and also try to install the package from test.py. But we will go on now and check that everything looks all right with the package on test.py. So here's this the project description, which is my package. I wasn't very creative, and I called it, this is the demo project for the 2021 Escape School. And you can see I am the maintainer. It requires Python 3.6 at least, and I linked the school repository here because this is where this comes from. And yeah, so I would call this a success. So what's the rest of the talk about if we are done now? This is what I mentioned. So you're not allowed to upload the same version twice for security reasons. So if you even just change a very minor thing or you have to fix something, you have to provide a new version number. Okay, so what's the rest all about? Yeah, we can do many more things. So for example, we can add entry points to our projects. And entry points basically mean you can define executables on the command line. So here I define a new entry point called Fibonacci, and I have to specify what Python script and what main function it runs. And this is in eSchool21 demo. In the standard main file, I want to run the main function. So let's look at this. Going back to this directory here. So in the eSchool demo, in this main file, I just added a simple command line script using this argument parser, and it takes as one argument on the command line the number of Fibonacci numbers we want to print, and then it goes ahead and uses our Fibonacci function to print all the first n Fibonacci numbers. And I now installed this package, and what it did is it put Fibonacci as an executable into my system. So I should now have, yes, I have Fibonacci executable here, and if I give it Fibonacci 10, it should print the first 10 Fibonacci numbers. And yeah, this will just call this Python script that we just told you, but it was installed into my path, so I can use it from the command line. And this Dunder main script in our package here is special because this is also the entry point Python uses when you give it the -m option. So if I do Python -m eSchool21 demo, this will also run this main script. So it tells me I have to give it the number, and if I do this 5, it will print the first 5 Fibonacci numbers. So this is very handy to have, so people can define this main entry point, which will be used for this -m switch, and you can define those entry points so that really these command line executables are installed in the system when you install your Python package. And this goes like this into the setup.config file. And then you might have the case that you also need to include, oh, this is an error on the slides. I'm sorry, I will fix this after the lecture, and we will see the examples how it's done correctly. So you want to include non-Python or non-C code into your package, and this can, for example, be some default configuration files or some data you need. And then you can put in setup.config this include package data equals true statement, and you can define that you want to include which data you want to include with the package. And if you look into the configuration of this demo project here, we have in our eSchool project here, we have this very important data here, and we want to make sure that this is also published along with our code. So in the setup.config file, we have now added configuration here. So we want to options package data, we want to include this information. So for our eSchool21 demo package, we include all the .dat files that are available. So *dat means it will include any of the .dat files in this eSchool21 demo repository. And here we also have the include package data statement. Okay. So like this, we can include arbitrary data files, and I will fix this example on the slide before I upload them again. And then we talked a bit about versioning, and this is also something we need to spend some more time on. So how do you define your package version, and what is this semantic versioning? And there's another PEP for this, so another Python enhancement proposal, which is the number 440 in this case. And this describes what are the allowed version number specifications for Python projects. And this looks a bit scary maybe, but it's not that complicated when you break it down. So I will ignore this first part because it's very rarely used by projects, but most projects just use this chain of numbers. So you have a number that can have arbitrary many places. So version 500 would totally be okay. And then you have a dot and then another number. And this can repeat as many times as you want. But the common convention we will see later is to use 3 groups of numbers. And this is the main version number of your software package. And then you can, for different reasons, also add some further specifications. For example, you can, if you are planning the next release, next stable release of your software, you can publish test releases for your users to experiment with and to report any issues they encounter before you actually publish the stable release on PyPy. And this is what these alpha, beta, or release candidate versions are for. So with an A, it's an alpha release. With a B, it's a beta release. Basically, test releases, which mean this is not yet stable, but you can try it out to see if there's any issues. And we want to have feedback on this software. And the release candidate is a very mature version of a new software, which is basically telling users, okay, this is basically what we want to do in the next version, but we are giving you the chance to test it. So please try out the release candidate and report any errors back to us or issues you encounter. Then there are the post versions, and post versions are there. So if you have an error in your build configuration or a typo in your documentation, you want to fix it, but you didn't change any of the actual code. So you didn't change any Python code, but you just fixed the typo in the README, or you changed your documentation system or something like that. Then you can do a post release, which basically tells your users you didn't change any of the actual important code, but you updated something else. And this is why this post release was done. And then there is other development releases, and these are basically very similar to alpha releases, but just another convention you can use, which is commonly used, for example, by systems which get version information from Git. They will do something like check what is the last version of the software and then count the commits that happened since the last release. And this is then called def 50, for example, if there were 50 commits to the main branch since the last release. And by default, if you just use pip to install a package, it will not consider these alpha, beta, release candidate, or def releases. You will only get the stable versions if you do pip install something. You have to add a special flag to allow these special versions for testing. And the most important thing about these versions is that they are solvable. So there is a clear rule how you can say that one version is newer than another. Okay, so let's look at this a bit. These are some versions your software could have, and these are in the sorted order. So this is sorted first by this major version, and then by the second, which is usually called the minor version. And then we have the bug fix release version if you use semantic versioning. And this is the last sorting order. And then we can see that these pre-releases are ordered before the main release, and the post-release comes after the main release without any specification. And development versions come before alpha versions, and beta versions come before release candidates, and release candidates come before the actual release. And then you can have a newer version that comes after the version 1.1. So semantic versioning is very useful because it makes it tremendously easier to tell if you can safely update to a newer version of a package when it is released. And there's a nice website explaining the concept, but very short. You have to give a 3-part version like this: major, minor, and patch. So 3 numbers. And projects increment the major version when they make API incompatible changes. So especially when you expect that your users have to change their code when they upgrade, you have to increment the major version. The minor version is upgraded if you make new features available, but basically keep all the old functionality the same, and you don't expect anything breaking for your users. And patch releases are for bug fixes, where basically nothing new is added, but only existing functionality receives fixes. And there are some caveats to this. So many projects in the Python ecosystem do use this semantic versioning, but many don't. So numpy is a famous example here. Numpy doesn't use really this semantic versioning and will make breaking changes between, for example, version 1.16 and 1.17. And also version numpy 20, 1.20 release had some breaking changes with respect to version numpy 1.19. So it's not using this system. And many projects that have not yet reached this 1.0 milestone basically shift this by one iteration. So they will make breaking changes between 0.15 and 0.16. And at some point they say, okay, we are now ready to release version 1.0.0. And then we promise to use this semantic versioning. So for example, GammaPy is now at the stage where we are very close to releasing this 1.0 release. And then we will promise to keep that 1.0 release working for you. And then you only have to worry about breaking changes once we release a version 2.0. And that brings us how you can specify dependencies. So if we now have know how these version numbers work, we can add different specifications for dependencies, which are also defined in this PEP 440. And these can be many things. So we can just plainly require the version, which does the package which does not specify any restrictions on this version. So any version pip can find will be okay, which will usually result in just the latest version being installed. And if there's a breaking change, then your software breaks. The next most common thing is to require at least some version, some lower version. So you, for example, know that you require features that were introduced in Pandas 1.0, then you want to require at least this version of Pandas. And Pandas, for example, uses the semantic versioning. So to make sure your code doesn't break, if Pandas 2.0 is released, you could require now that the Pandas version is also smaller than the first alpha release of Pandas 2.0. This is basically the same here. So if you require a version that is equal to 1 with a star, this will mean any 1.x version is allowed. And there are different specifications here. You can also exclude specific versions where you, for example, know this one had a bug. I don't want my users to install this, then you can exclude it with an exclamation mark. And very handy is this notation with the tilde, which is the so-called compatible version specifier. And that means we should have at least 1.1, but any 1.x version higher than 1.1 is allowed. And this will take, so to say, the most significant, the least significant digit here. So this would require any 1.1 version larger than 1.1.2. So for example, 1.3 would be okay, but 1.2 would not be okay because we required that it should be compatible to 1.1. Another thing we can require is what we also talked about in the testing lecture are optional dependencies. And if we have optional dependencies, we can define these as extra groups. And then people can install our package specifying what kind of optional features they want to use. And this is very commonly used, for example, to tell your developers what they need to install to run the tests or to build the documentation. And it's very common convention, and I would highly recommend to all to use this to also specify an all target. That just means give me any of your optional dependencies. I don't care if I install a bit too much stuff that I maybe don't need, but I just want to make sure I can run all the features of your software. So we define that we need PyTest and PyTest-Cuff for our test suite. We need Swings for the documentation. And then we use these previous definitions here in the all section to define, okay, yeah, for everything, this is a tests plus the box and any other optional dependencies we might also declare here. And then our users can add this in square brackets here. For example, I could pip install CTA pipe all, and then I get all the optional dependencies as well with CTA pipe and not just the core required dependencies. One common issue then is if you specify the version of your project, you probably need that at many places. So at least at 3 places that come to my mind. You will have the package version in the package metadata, which we saw in the setup.config. You will want to usually make your version also accessible in the code so that users of your module can check what version of your code they are currently running. And this is in Python by convention done by adding a dunder version attribute to your module. And then you will also create a Git tag for any release version. So you have now 3 places where the same version number is stored. And this is not good because you can easily make mistakes and have a situation where then these 3 places don't match because you forgot to update one of them. So there are some tricks to avoid this duplicated definition of version numbers. I will show you one that gets rid of one duplication here. So these 2 here will have a common source, but you still have the Git tag. And then there's a setuptools SCM, which is a really nice package to completely automate this. But because of the short time, I will not go into detail here. You can check the documentation or the AstroPy or CTA projects which use setuptools SCM to build their version numbers. So the simple solution for setuptools is to just specify the version in your init file using this convention to call it dunder version. And then you can, in the setup.config, declare that your version is this attribute of your module. And the great thing is that this even works if you, for example, import numpy in your init.py and numpy is not installed, because setup.py will not actually run your code, but it will just parse your code using something called the abstract syntax tree of Python and get this variable value without actually executing your Python script. Okay, so let's very quickly talk about some of the common software licenses in open source software. And the usual disclaimer, I'm a physicist by education, I'm not a lawyer. So if you have important projects that maybe affect also the outreach of your institution or university, please talk to your legal department before just copying any of my stuff here. But in general, software licenses have 2 main purposes. They define what other people are allowed to do with your code, and they usually contain sections like this software is can be used by you, but I'm not liable for any damages you bring up on yourself by using my software because of any bugs or so. So it frees you from liability and for damage claims when somebody uses your software in a wrong way or you had a bug and that created problems for someone. And there are several standard open source licenses that are different, but declare very similar things usually. And there's the open source initiative, which classifies those licenses. And if you are interested in this, I would highly recommend you to go to the website of the open source initiative and have a look through their approved licenses, which range from very short to very long, from very restrictive to very permissive. And usually when we talk about free and open source software, we don't mean free as in beer, like it doesn't cost you anything, but we mean free as in freedom. So you are free to do with it whatever you like or what is allowed by the license. You can change the code, you can look at the code, you can run it, you can modify it, you can share it with other people. So this is the kind of freedoms we are talking about here when it comes to free software licenses. Okay, this is the only license I think I have ever read in its entirety. This is the MIT license and it fits on this slide. It is one of the very permissive licenses. It basically grants every right to use to other people and has this disclaimer here at the bottom that you're not liable for any of the damages people might get from using your software. There are more complicated licenses, and the most famous examples here are the GNU public licenses, GPL and LGPL. And these are special because they have the freedoms we usually associate with free and open source software. So they allow redistribution, modification, and running of the software. But they require that if you make modifications to that software or distribute it yourself with other software you made using this software, you have to use a similar license or the same license. So you are not allowed to charge people money for your proprietary source code when you use a library that is under the GNU public license or the lesser GNU public license. And there's some debate I won't go into here about whether linking to shared libraries is allowed or not. And this is the reason why there's a GPL and an LGPL. You can read about this on Wikipedia for these two licenses. This is all I have time for here. So my recommendation would be to choose one of the more permissive licenses like the MIT or the BSD licenses. And I think I won't have to go into any more details here. Please just watch the keynote addressed by Rachel, which went into much more detail than I can go into here with all the important points about reproducible and open source software in science. Okay, I see I'm basically out of time, so I don't want to go into all the details and do the live demo here for the binary wheels, because many of you won't really need this. You will probably only write Python code or number optimized code and don't really write your own C or C++ libraries, but you can check this afterwards with the demo project and the further reading I linked in the back. So again, the idea is here that we have code that uses cython, which is another method to create fast code from something that looks like Python code. So it basically transforms your Python code to C code and then compiles the C code, resulting in very fast code, which can even be faster than number. So I made some sample tests with some library some time ago, where I used both number and cython to optimize it. And both results were really fast and much faster than the Python code, but the cython code was even faster, I think by roughly a factor of 2 than the number code. That being said, using number is much more convenient because it doesn't require this ahead of time compilation, but just this just-in-time compilation. So it's much more, so to say, user-friendly. So if you use Cython and also then want to use the NumPy C API, so you can also use NumPy from C to build your C extensions to Python. We basically need to say in the pyproject.toml file that we need Cython at the build time, and we want to compile again against the oldest supported version of NumPy. And this is again the reason we want to support as many users as possible. And NumPy is forward compatible. So if I compile my code with a very old version of NumPy, it will work also with newer versions of NumPy, but not the other way around. So if I on my system compile my extension against NumPy 1.20, it won't be usable by someone with NumPy 1.19. But the other way around, if I compile with a very old version of NumPy 1.16 or 17, then it can be used by all people that are using NumPy 1.17 or a newer version of NumPy. And this is why there's this package on PyPy called oldest supported NumPy. So we can use this in our build configuration here to compile against that oldest supported version of NumPy. And then we have the 3 main operating systems. So on Windows, everything got a lot more simple with Python 3.5, which is now also not supported anymore. So basically, we also only have to care about Python 3.6 and higher. So the situation is much simpler now. We have to install the Visual Studio C and C++ compilers and the Windows SDK. We need to install all the versions of Python we want to support, and then we just use this wheel building command we saw before for the non-compiled extension to build our wheels, and we can just upload the resulting wheels on PyPy. And this will then have these Windows tags and the Python version tags, because they are only compatible with a specific version of Python and a specific version of an operating system. But when we do it like this will work for all Windows versions and all the Python versions we use to create the binary wheels. On macOS, the situation is similar. So you have to install the compilers using Xcode. This is the command you also use to install Git. This will also install the C compiler. And then you need to, again, install all versions of Python you want to support. And this is most easily done on macOS using brew or pyenv. And you have to, with an environment variable, specify the oldest version of macOS you want to support. So this macOS deployment target means that we want to support any version of macOS newer than 10.9. And again, we use Python -m build to build the wheel for all our versions of Python, and then we can upload them to PyPy. On Linux, so the story is a bit more difficult, like I said, because of all these different Linux distributions. And in the end, it boils down to the version of the C standard library, so the glibc you want to support. And there are different standards, and these basically refer to specific operating systems that have then specific versions of the C standard library, or in newer times, also we just specify this version of the glibc. And one of the standards I would currently recommend to use is this Many Linux 2014 standard, which is based on CentOS 7. So the Red Hat Enterprise Linux binary ABI, which is from 2014 and then runs on all systems newer than this version. And there is a good demo project that uses Docker to build this kind of Python wheel for a demo project, very similar to the demo project I have in the Escape School repository. It gets a bit more difficult on all the operating systems if you have external dependencies. So if you don't just have your own C extension, but you depend on some C library or C++ library, you need to include this in the wheel. So wheels are only allowed to depend externally on very few standardized system libraries like the glibc and the OpenSSL libraries, I think, and they are all mentioned in the two PEPs I linked above here. And for all other libraries, you have to include them in the wheel file. And there are two tools for this: audit wheel on Linux and delocate on macOS, which scan your wheel for any external dependencies and then include those into the wheel and create a repaired wheel. Unfortunately, there's currently no off-the-shelf solution for this for Windows, so you're basically left on your own if you want to build wheels with external library dependencies on Windows, which is a bit unfortunate. Okay, so and then there is a CI build wheel project, which basically automates all this stuff away in a CI configuration if you really want to do this. But the manual step would be to run the Many Linux Docker container and then use this audit wheel repair to, with the given platform specification you want to use, which you can apply to your wheel, and then you will get a repaired wheel as output, which you can then upload to PyPy. Okay, I will skip the poetry part because I'm out of time. I will just note that this is an alternative to setuptools, and you should look into it for your Python projects because it has this so-called log file, which makes it easy to exactly reproduce a programming environment. So go through the bullet point list here, check out the documentation. I will not go into detail here. I underestimated a bit the time I will need. Okay, and I will also skip the live demo part. Here we can do this maybe later if you're interested. If you have a specific Python project you want to deploy, there will be many specifics here, and you can try out the demo project in the school repository first. Yes. So if I am allowed to take maybe 2 minutes more, let's also talk a bit about Conda packages. Conda packages are another abstraction layer. Conda does allow you to also build packages not only for Python, but for any kind of library, for any kind of software. So for example, if you are accustomed to this R programming language, which is very well known in the statistics community, Conda also has packages for R, for example, not only for Python. And it's very easy to build a conda package when you already have this working setup tools set up. You basically just need define a meta.yaml, which is again this kind of configuration file we have now seen 1,000 times, where you have to give specific options that tell conda about how it needs to build your package, and then you can call the conda build command and the conda upload command to upload it to your channel on conda. And there is this very, very, very great effort of the open source community to automate this and provide hosting for this. This is called Conda Forge, and this makes it really easy if you have already this setup tools setup working to publish Anaconda packages for all operating systems and all Python versions you want to support, even if you have complex dependencies. So I just made this for CTA pipe, for example, and for another more low-level C++ library also used by CTA, and this was really easy. As soon as you have this setup.py step working, it's really easy to use this Conda Forge infrastructure to build your Python packages for Anaconda. Okay, so let me finish with some general recommendations. So the first step should be that you make sure that your code is a valid Python package and that it declares its dependencies using the setup.config and setup.py we knew. And if you have this on GitHub, people can just pip install your module using the GitHub URL or the tarball from GitHub. But even better then would be the next step to upload your source distribution and the any wheels to PyPy. This is free and very easy. You saw me do it in like 2 minutes using this twine command, and I had it up on the test PyPy channel. And then your code is just a pip install away. As soon as you have did this, everyone in the world can pip install your module, your code, and can run your analysis or use your library. And this should be done using one of the permissive open source licenses. So the two most well-known examples here are the MIT or the BSD3 clause license. You can look them up. They are very short. You can read them in like 5 minutes and probably agree with all that is said there. In our community, using Conda is very common, so it might make sense to also publish a Conda package. And for this, please don't worry to do this manually. Look up Conda Forge, how you can add a new package to Conda Forge. This is much, much easier than doing it manually. And then when you have compiled code, you should look into this story of publishing binary wheels and Conda packages, because this will so much ease the installation process for your users. So a couple of years ago, basically, it was very, very hard to get to run anything from the Python scientific dataset on Windows because it was such a mess with all the compilation. And this is basically the main origin story of Conda. Conda first had the ability to provide these pre-built binary packages for Windows, which made it much, much easier to use it on Windows. And nowadays we have the binary wheels. And also if you now do pip install numpy or pip install matplotlib on Windows, it will just work and take a couple of seconds for the download, but then it's basically done instantly. And for packages that are not using any of these compiled components, I would highly recommend to you to also have a look into this new Poetry package manager. It has some very nice properties. For example, this automatic creation of virtual environments with all your dependencies, and this log file, which really pins down your dependencies to the exact versions you have verified to work. And all this is only possible because of the many, many improvements over the last recent years. If I would have to give this talk 5 or 10 years ago, it would basically be impossible to cover a working Python packaging installation in just 1 hour. This has really, really greatly improved, and we are very lucky for all the people that contributed these nice solutions we have now. And this is just for you some further references you can check. So there's a nice user guide, which I used as source for this presentation. There's the setup tools documentation, the Poetry documentation, the Conda documentation, and these tools to get you started with the compiled wheel extensions. Sorry for taking 10 minutes more.
No problem, Max. Thanks a lot.
I still can't hear you, unfortunately.
You cannot hear me yet? No? Okay, so it will be at Okay, so you cannot see us, but I hope you can hear us. Okay, hello. Okay, so there was a couple of questions raised in the chat.
Okay, now I can hear you.
Max, so I think that this should be underlined and clarified maybe in the live. So, for example, which is the difference between specifying when speaking about versioning the delta equal 1.1. I don't know how to say that. That's symbol like the approximate equal 1.1 and the larger equal 1.1 versions, because they seem to mean the same thing.
Okay, so we are talking basically about this here, right? So
yeah, exactly.
Exactly equals 1.1
so
and this operator
5
here.
And 6.
Yes.
So 2 and 5 basically.
Yes. So 2 and 5. So this one only allows versions that start with a 1, and this would only also allow 2 or 3 or any newer version. So this doesn't restrict on any newer version, but this means at least 1.1, but not anything that is not a 1 at the front. So it's more restrictive. It means any of the 1.x versions, not any 2.x version.
Okay, perfect. Thanks. So that's pretty much all. There were not more questions in the chat, so thanks again for the this nice explanation. I think it was very clear for everybody. So we'll be closing here the session. Thanks a lot, everybody. Thanks to the speaker, especially to Max, and see you tomorrow at 9. I think as every day. Thank you. Bye.